So on plan book, I made the slight shift to where what we're going to be doing today is I'm going to do my next example of the relative motion we talked about yesterday because I know it was so fun. Um, and then I'm going to give you an opportunity to see how you, if you want to, with a partner, work on three problems that I'm going to show you work. Okay. After some time, I will kind of have us all reconvene. We'll go over those three because they were going to be the original homework problems that you're supposed to do last night, but decided, we'll just work on them in class today. Um, so we'll do that. We'll talk about those three problems, and then I'm going to show you about a 6-minute video on what we're going to be getting into in tomorrow's discussion. Okay, so we will actually be getting into 4.1 tomorrow. Okay, this is where you get to draw your pictures, and then 4.2 will be Monday. So you'll be having a video sent out on Monday. Okay, so be looking for that along with the homework assignment. Okay, and I'm not going to put the homework assignment on, you're not going to turn it into Classroom. Okay, you don't have to print it out at home. I'll give you the sheet. You don't have to print it out because I don't ever really need to collect those. You can just put it up on your computer screen and work on it from that. Okay, write your answers on a piece of loose leaf. You'll turn that in on Tuesday in class. So, so that's kind of what the plan is going to be. The quiz is going to remain the same. Okay. But it'll be on Tuesday, but it may, no, I don't think it's going to be a paper copy. Okay. Because you'll be drawing on it. So, yeah, I guess get your notes out. While you are watching that video towards the end of class today, I'm going to come around and give you your chapter 4 materials. Okay. All right. So yesterday we ended talking about the moving walkway and the gentleman running down that moving walkway, and we compared how much time would he actually save by running in addition to the moving walkway compared to just running on normal ground. Okay. Now in yesterday's, we didn't really have to do too much in terms of determining the overall magnitude and direction because they were just simply running essentially parallel with each other. Okay. In the example I'm going to show you now, it's going to bring us back to our 3.2 roots where we use Pythagorean theorem and the inverse tangent. Okay. So we have a boat, okay, heading north. It crosses a wide river with a velocity of 10.00 kilometers per hour relative to the water. The river has a uniform velocity of 5.00 kilometers per hour due east. We are to determine the boat's velocity with respect to an observer on the shore. And so it doesn't tell us directly, but within that last statement, determine the boat's velocity with respect to an observer on shore. That's going to kind of force us to give the magnitude and direction. Again, it doesn't say it in here, and if you ever asked later on by me, I try to tell you exactly what I'm looking for, okay? But if we go ahead and, let's draw a picture of this. You know how I like to draw pictures, okay? Hello. Okay. Let's draw a picture. So Again, one of the best things to do is always do a coordinate system. Okay? I'm already off to a great start. All right, so, and just so you can see this, I'm going to move it off of the origin a little bit. It doesn't matter, okay, if it's on the origin or not. All right? So, I got a person who is standing on the bank. Okay, you know what a bank of a river is? Okay, this is the bank. All right, and they are saying hi to the boat. Okay, you had a boat that went across the river. So if you think about what you heard, across the river and the river is flowing due east, you can make the assumption, if it's not told to you, that it is traveling north. Okay, and it was traveling. Here's a boat. Oh, boat. Okay, at 10 kilometers per hour. Okay. The river traveling due east. What was the river's velocity? 5 kilometers. Okay. So we need to figure out, with respect to this person on shore, what is the boat's velocity, overall velocity, and direction. So how would this observer see that boat traveling? Okay. Well, we got to start developing a formula here. Okay. So we have the velocity of the boat, the velocity of the water, and the overall velocity of the boat to the observer. Okay. So let's look at the velocity of the boat. How could we name that? Okay. We got the velocity. Since we're talking about the velocity of boat with respect to the water, okay, because that's how we're kind of figuring out how fast we're going. We have the velocity of the boat with respect to the water. Okay, VBW. It has a velocity of 10 kilometers per hour, like we mentioned. And I can't stress this enough. Don't sweat too much on getting the formula set up. Okay, don't sweat too much. I'm just showing you based off what we did in this section. All right, the next velocity we have is going to be water in comparison or in relation to the earth. So water in relation to the earth. And so that was 5 kilometers per hour. If I can't. Okay. So now our unknown is going to be between the boat and the earth. So if we set up this equation, the reason why it's between the boat and the earth, because look, as we saw yesterday, the first one and the last one of the two known become the subscripts on the unknown. So VBE is equal to VBW plus VWE. Again, W's, we use the last or the preceding subscript as the first letter in our next subscript there. Because all this really becomes is a simple problem that you should recognize. Okay? If we look back up here at the motion of the boat in the water, what shape does it form? What type of triangle? Right triangle, right? I mean, correct? So, that means that we can use the old Pythagorean theorem. And so if we have c squared is equal to a squared plus b squared, all these really equal are just the a and b, right? So, again, in order to find our unknown, or our c, or our VBE, take the square root of our two velocities squared and then sum them together. So our 10 kilometers per hour squared plus our 5.0 kilometers per hour squared. Can anybody tell me what, and if you put this in your calculator, what your overall velocity will be if respect between the boat and the observer on Earth? Very good. Very good. So there's our velocity. We're not quite done yet. This right here is our, you can't even see it, is our theta, okay? Right there. So if we take the inverse tangent to find what angle and what direction that is, you're going to have 5 kilometers per hour over 10 kilometers per hour. So what is our angle going to be for our theta? Very good. 26.6 degrees. And to describe the actual direction, you could say east of north, or you could do east of north, however you want to. Oops, you can't see that. Okay. East of north, east of north. So that's what you would have to do to do this. So again, it's just the most confusing part. And you can probably tell that this is not my favorite talk about relative motion, but again, it does get you to try to think about frames of reference and how things move and operate depending on where you are. So what I want you to do is I want to see how creative you can be, how you can pick through some of this craziness. And if you open up your books to page, I forgot what page it was now. I didn't put it. When did I put it in here? No, practice F. And that is on page 105. Page 105. And I want to see what you can do with questions 1 through 3. So again, you can work on your own. You can work with one partner. And we'll take about 10 to 12 minutes on this just to see where we're at.